Good morning and welcome to our MAST series of online seminars. And today we are happy to welcome Dr. Vladan Stevanović from the Colorado School of Mines and the National Renewable Energy Laboratory. Vladan was born in Serbia, where he did his undergraduate degree, but then he did his PhD work at Lausanne in Switzerland. And after finishing in Switzerland, he became a postdoc, as I understand, in the U.S. And he was a postdoc. I believe his first postdoc was with Alex Zunger at the National Renewable Energy Laboratory in Colorado. But soon after this, Alex left this laboratory, and Vladan was hired there as a staff member. But soon enough after this, he also became a professor at the Colorado School of Mines in the material science department. I don't know how exactly it's called, materials engineering department, but he's still affiliated with the National Renewable Energy Laboratory. He's well known for his work on first principle modeling of a number of materials, ranging from semiconductors to spinels and some oxides. In more recent years, he started to study also amorphous systems, which has usually been a challenge for first principle modeling, but he has produced some very nice, interesting results that we are really looking forward to hear about today. So without further ado, Vladan, welcome.
Thank you very much, Vlad. Thanks for the opportunity to present my work here in the MAST seminar. And before I start talking about metastable states and then metastable materials, just to say a couple of words about what we do in my group. So we are primarily a theory and, let's say, computational group that does first principles calculations, but we work within the field that is kind of colloquially known as materials discovery. So we are trying to pretty much address the question that experimentalists usually come to us with, which is what should we grow next? So in a nutshell, that's what we are trying to address. The field or the class of materials that we work on are known as functional materials, so semiconductors, but not only semiconductors. And when answering the question of what shall we grow next, I mean, the follow-up question to that is the material that you are proposing us to grow stable or not. So the questions of materials, thermodynamics, thermochemistry, stability, and so on are kind of essential to materials discovery. And I've been working on that problem since long time ago, since I joined NREL about 15 years ago. And then questions of stability naturally lead into questions of metastability, and that's the topic of the talk today. So we started working on identification of likely metastable and useful metastable states of solid matter about 6-7 years ago, and I will kind of give you an overview of what we've done. So why should one care about metastable phases? Well, first, it's a very interesting scientific problem, how to identify the truly metastable states of matter. And in this picture, you see a more practical reasons why. So these are the examples of 3 systems that we kind of see on a daily basis that are all metastable forms of matter. Diamond, I think, is a prototypical example of a metastable crystalline phase, or a polymorph, if you wish. Solid chocolate is another one. So the polymorph 6 of cocoa butter is actually a metastable state of cocoa butter, and that's the one that is the most expensive and the most pleasing for its textural and whatever taste properties. And then glass is another very common metastable form of matter. So the question I will be discussing today is really how to identify, using computations, useful, experimentally realizable, and long-lived metastable states. With regard to the useful part, I think we came a long way in developing computational methods and theories and we are now able to, with a high degree of certainty, to calculate a range of properties of pretty much any arrangement of atoms for large classes of chemistries and large classes of crystal structures. So I would argue that addressing the useful part can today be done with a relatively high degree of certainty. The questions that I'm going to discuss here really pertain to experimentally realizable and long-lived metastable states. So why would one care about experimental realizability? Well, there are in principle infinitely many metastable states, unlike stable or the ground states that you can find one or maybe a few if it's degenerate. But metastable states, there is a sizable spectrum for each chemistry. So how to identify which one of those are going to be experimentally realizable? Because if you go to experimental literature, you actually find that only a fraction of those has ever been synthesized. So is there anything like some kind of underlying principle that will sort out those that are more realizable and less realizable? One that will be extremely helpful and useful for the identification purposes. And then, of course, metastable states have finite lifetimes. So in order for them to be useful, we really need to kind of have the ability to single out long-lived metastable states. And I would argue that presently we are not very good at either realizability and the lifetime of metastable phases. So that's what we focused on, what we concentrated on, and where I would argue, made some progress that I will be telling you about. So the first topic is this experimental realizability of polymorphs, of how to go from many low energy local minima on a potential energy surface to a few more realizable ones. Typical story that we tell to students in our courses about metastability and polymorphism in particular is that of a kinetic trapping. So we tend to represent the different states on a potential energy surface where different local minima represent likely metastable states. So for example, ground state here on this picture is P0, and then we will have polymorph 1, 2, 3, 4, and so on. So the kinetic trapping pretty much means that if you can create some kind of experimental conditions to get your system inside one of the polymorphs that is not the ground state, let's say P1, and if that local minimum is deep enough, then after removing whatever perturbation we applied onto the system to get it into P1, if the local minimum is deep enough, then the barrier to go from P1, let's say, to P0 will be large enough so that at ambient conditions it will survive, even though it's not the ground state or the minimum of the corresponding thermodynamic potential. However, this story, while I have no problem with this story is qualitatively correct. In my view, this story doesn't tell us how we get into P1 and what is the likelihood to get into P1 to begin with. So the quantity that I'm going to discuss that has to do with the likelihood of getting into different local minima is not the depth of a local minimum, it's actually the width of the local minimum, or the more mathematically precise formulation is the volume of configuration space occupied by the basin of attraction of that local minimum. Why would that quantity have anything to do with the likelihood to realize a certain polymorph? Well, the width of the local minima would measure the probability to fall into that local minimum. And the initial hypothesis that we made was that those that are wider, meaning have higher probability to fall into, will then be experimentally more realizable than the others.
Vladan, may I ask you?
Yes. Yes.
So when you say a width, you are I think you are implicitly assuming that before you form these states at high temperature, that all configurations are equally probable. So if you just count the number of configurations in a certain valley, then they are, the probability of having them created is proportional to the number of these configurations. But in some correlated liquids, like for example, hard sphere liquids and so forth, they are the number of configurations that exist in the liquid as opposed to the gas is much restricted. And it's not completely
Sure.
obvious that, and so what do you think about this in this context?
So I think you're correct, but I would like to focus here really on the probability to fall into a given hole. So I'm not gonna assume any precursor state for this experimental realizability. I just want to measure the widths, or yes, the number of configurations that belong to a given local minimum, and try to rank different polymorphs based on just this quantity, and then compare with whatever has been seen experimentally for various systems. So that's where I'm going, and in that I will refrain from any philosophical point of view on what the precursor may be. Is it high temperature, liquid, gas, whatever it is. I'm not sure that I answered your question, but that's the starting point.
Yeah, I think it's clear. Thank you.
Okay, some of these things have been discussed previously by Stefan Gedeker from Basel. You have here the reference. We kind of came with this idea and hypothesis independently, but then found in the literature pretty much only one mention of something similar, which is that paper from 2014 in the context of metallic clusters. So then the question really becomes how one measures these widths, and it may actually is easier than it may seem. And the idea is very simple. If you have a system of holes in the ground, how would you measure their relative widths? Well, you let it rain for a while, and then after a certain amount of time, you just measure how much water there is in each well. So in the context we are dealing with here, this kind of raining could be realized by a structure prediction method pioneered by Chris Picard and Richard Neitz from Cambridge, called random structure sampling. They actually created it to search for the ground state, but the random structure sampling can actually provide a statistical representation of the potential energy surface, and it pretty much works as follows. You basically create a random box, so random unit cell parameters, and throw atoms randomly inside the box, and then use first principles methods to relax that structure which has periodic boundary conditions imposed on it to the closest local minimum on the potential energy surface. So once created, these random structures will be somewhere at the slope of the potential energy surface, and then using first principles relaxations, they will relax to the closest local minimum, let's say P0 in this case. And if you do this random structure generation followed by first principles relaxation enough times, then you can just count how many times you landed in this structure, that structure, or the other one, and count, and those counts or the frequencies of occurrence in random sampling would represent the measure of a width of a local minimum. So just as an illustration how one of those random structures may look like, so this is a 40 atom, let's say zinc oxide random structure. We created our own random structure generator that try to intersperse cations and anions whenever we are dealing with ionic systems like zinc oxide. So this is one example of that. And then after the relaxation, this particular one really relaxes to a supercell of the ground state Wurtzite zinc oxide. So again, just an illustration, we will be generating thousands of these, doing the relaxation, and then counting how many times we end into Wurtzite or zinc blende or rock salt or the other ones.
Couldn't you say, how do you actually generate the initially random position? Because it seems to me picture you cannot, they are clashing with each other. They're not completely, you know.
Okay. So let's call it a quasi-random, quasi under quotations. So what we would do, we would choose a random ABC alpha, beta, gamma lattice parameters within some reasonable bounds. So we will not allow angles between unit cell vectors that are 1 degree or things like that. So we will create more or less some kind of box that is reasonable. And then we would throw atoms randomly on a grid of points that is inside of a box. And then each occupied grid point, we would put a Gaussian. So the code that I wrote puts a Gaussian on each occupied point, so that the next point is chosen randomly from the collection of grid points that have the value of the sum of the Gaussians, you know, below certain value. So in that way, we would prevent atoms on top of each other, and we would also introduce some kind of a distance that we can regulate between the atoms. Does that answer, Vlad?
Yes, so that's some form of short-range order that you are already putting in.
Yes, there is a little bit of a bias, but other than that, we've done a lot of testing over the years, and other than those biases, we were not able to identify any other biases. So they are, let's call it again under quotations, random enough.
So this relaxation is done from the first principles, or?
Yes, using density functional theory, just standard. We would be dealing with very relatively simple, chemically simple systems and electronically relatively simple systems. So in that sense, we would just be using generalized gradient approximation and some kind of Newtonian relaxation method. Does that answer? Okay. So then initially, we really tested this hypothesis on just a few very simple systems. So what I'm showing you here are the results for magnesium oxide and zinc oxide. 2,000 random structures were generated for each of these. And then these plots show relative frequency of occurrence in the random sampling of different structure types, different local minima, as a function of energy on x-axis. The numbers here represent the international space group numbers. So the space group 2 to 5 is the rock salt, 194 is, I believe, nickelin, or some version of 194 is the nickel arsenide one, 216 is zinc blende, 186 wurtzite, and so on. And in both of these pictures, what you can, I think, very easily recognize is that at the top of this of the y-axis, you have, in case of magnesium oxide, just one structure that occurs around 50% of the time. So the y-axis is logarithmic scale, 50% of the time. And then after that, we have like different other structures occur, I don't know, 2% and or less. This thick line here are the structure types that occur only once. Many of them are just low symmetry ones. In the case of zinc oxide, what you find is the group of 4 structures that occur more frequently than the rest, separated by about a factor of 10, so an order of magnitude in occurrence, so from like 3-4% all the way to about 11%, whereas everything else is a half a percent or less. So there is a clear distinction in these two systems between low occurring and high occurring structures. In the case of magnesium oxide, this one that occurs 50% of the time, so literally 1,000 times out of 2,000, is the ground state rock salt structure. And this fact corresponds very well to the experimentally known fact that magnesium oxide has been realized experimentally only as a rock salt and nothing else. So magnesium oxide doesn't really have any polymorphism. So no structure other than rock salt has ever been grown. And magnesium oxide is a fairly mundane system. It has been grown zillion times with many different techniques, and no one ever found anything but rock salt. So this result kind of is in pretty good correspondence with experimental facts. For zinc oxide, the story is the same. Out of these 4 structures, one of them, this one in gray, is a tetragonal, some kind of tetragonal structure, but that one has imaginary phonon modes. So that's why it's in gray. So it's a dynamically unstable structure. So out of the 4 highly occurring ones, the 3 that are in red that are not dynamically stable, not dynamically unstable, are the ground state wurtzite, the zinc blende structure, and the rock salt, the 3 known polymorphs of zinc oxide. So this again is pretty much one-to-one correspondence with the experimental facts that are known about zinc oxide, another system that has been grown many times with many techniques. So it's not that we are missing something experimentally. So this was a very nice initial kind of, let's call it, proof of concept or validation of our initial hypothesis. Since then, we have tested this on around 30-ish system, between 30 and 40 actually. And whenever the system is not so complex that we can actually converge the random sampling, the result is always the same. So in my mind, this hypothesis has been well validated by now. This paper has been published almost 10 years, 10 years ago. So one could then ask, okay, fine, is there any way one can formalize and find where formally these widths of local minima actually enter the theories we use to describe phenomena related to potential energy surfaces and growth and so on. So that's not actually hard to show if we assume classical ergodic system. Now we are going to assume, Vlad, some kind of a liquid or a gas phase or something. And then the partition function of such a system is proportional to the Boltzmann exponential of the potential energy surface, and the integral of it actually over the entire configuration space. And then one can, as it's usually done, separate this integral. So split the domain of integration into different basins of attraction and just express this integral as the sum over different basins of attraction, where now within each basin you have the corresponding integral. So if one makes just approximation like this, so going from the actual potential energy surface into some kind of a square well approximation, then within each well, the energy assumes a constant value. So it can be taken, so the exponential can be taken in front of the integral with a value that corresponds to the actual value at the local minimum. And what remains then under the integral is nothing but the volume of configuration space occupied by a given basin of attraction. So essentially, the partition function kind of breaks into a discrete partition function of a discrete set of energy levels, where these volumes of each local minimum appear pretty much as degeneracies. So our argument is essentially an entropy argument. And those degeneracies pretty much appear in what we would normally refer to as the ensemble probabilities in statistical mechanics. So and the ranking that I showed you on a previous slide was pretty much done exclusively on these omegas. One can then ask a question, okay, what if you bring the energy into the picture, and how would ranking look like if you now rank systems based on full statistical mechanics ensemble probabilities? And we did that on elemental carbon and silicon carbide. So what I'm showing you here is the ensemble probability distribution calculated at room temperature. Again, temperature doesn't really affect the ranking. It will broadly affect how much in probability two points are differ between each other, but not their relative position in probability. So room temperature is just something that we assumed. And that probability distribution is shown against the volume of each structure. And here for elemental carbon to the left, you see in yellow, there are many yellow points, which is the very low symmetry or space group number 1 and 2. And those that are colored are then have space groups that are then labeled in this inset. And for elemental carbon, by the way, relaxations here were done with van der Waals corrected functionals. And this distribution, if you analyze it a little bit more carefully for carbon, you will identify kind of two peaks where you have a denser peak, or the lower volume peak, and a higher volume peak. And if you look at the top of these peaks, you find what you expect. At denser peak, you find diamond at the top, and then hexagonal versions of diamond, so space group 166, space group 194. And in the lower density peak, at the top of the peak, what you find are different ways of stacking graphene sheets, so into graphite. So you pretty much find graphite and diamond as known experimentally. And again, we are reproducing experimental results fairly well. Silicon carbide distribution of probabilities is markedly different. It has only one peak now. And at the top of that peak, what you find are, again, expected structures. You find space group 216, which is the zinc blend, followed by wurtzite, which is another known polymorphs of silicon carbide, and the space group 160. That's another known polymorph of silicon carbide. And again, they are well separated from the rest. Two questions come to mind from this slide. The first one has to do with the fact that the rock salt, which is shown here for silicon carbide, is a high pressure phase of silicon carbide, known high pressure phase. And it is kind of shown here, or it shows up in this distribution at a very low probability. The reason for this is that now we are bringing energy into the picture that depends exponentially, the probability exponentially on the energy. So energy difference between the rock salt and zinc blende ground state is relatively large. So that's why the probability kind of tanks, especially at room temperature, for the rock salt. What one can do, put enthalpy instead of energy into the Boltzmann exponential and then increase the pressure. And what you will see then is that at a pressure of about 50 gigapascals, 60 gigapascals, I think, the rock salt will become the most probable structure. And by the way, 60 gigapascal is about the transition pressure between zinc blende and rock salt. Another question that may be interesting to discuss is that both of these probability distribution kind of tilt to the right from the essentially diamond structure. So zinc blende is just diamond occupied, populated with two types of atoms. And there is a diamond structure here. So essentially the whole potential energy surface, as represented statistically by our random sampling, seems to be leaning toward less dense structure or high volume structure. And one can then ask, is there any implicit bias in our random sampling? I will discuss that on yet another system, so elemental silicon, which again has a diamond structure.
Go ahead. Question.
Yes.
Go ahead, Vlad.
Yeah, so it's interesting that for carbon, you can see that the volume width of this distribution is not too different from the difference between the two periodic polymorphs, the graphite and the diamond. So you can say, well, most amorphous structures are a mixture of the two of some kind. But for the other one, you have for silicon carbide, you have only one peak, periodic peak, and then there is a broad distribution which is mixture or admixture. So the question is, can you think of these other amorphous structures as a mixture of periodic structures, or they're something completely different?
So first, this sampling was done, just a clarification first before I answer. This sampling was done on a relatively small number of atoms, so 12 atom periodic cells. So each of these structures are periodic. It's just that some of them have higher symmetry, some of them have lower symmetry, which are the yellow points. I will get to the question of how one represents amorphous toward the end of this talk. But yes, I think your assumption is correct. If I'm interpreting what you said, Vlad, correctly, that you could in principle think of the amorphous structure as a mixture of these points.
Yeah, I have a question about how about the temperature? This is only shows the as a in a space
at
of
room temperature.
In terms of at the room temperature. Okay.
Yes. So this probability distribution has been calculated at room temperature. If you were to increase the temperature, the only thing that will happen, you will squeeze this distribution to a narrower range on y-axis. But if you look exactly the same. So the ranking of different structures will be exactly the same.
Okay. Yeah, I would imagine there's another dimension is pressure, right? It just
Yes, correct. So yeah. I'm going to discuss that next. So if we go to elemental silicon, now we have slightly larger cells, so 24 atom cells. Again, I am sweeping under the rug and not discussing really convergence of all these results. So we are assuming that these are well converged, and we are doing our due diligence to converge both with respect to the number of structures and with respect to the size. So we can discuss that more later if you wish. But so this is the probability distribution, again calculated at room temperature for elemental silicon. And the first thing that is kind of noticeable is that the ground state diamond structure of silicon appears as the highest probability, as one would expect, because it's a ground state structure, it's a low temperature Boltzmann factors, so it's kind of going to dominate the probability. But then the distribution now tilts to the left, not to the right as in silicon carbide. and graphite. So this kind of shows that there are really no biases in our random sampling towards less dense or more dense structure. Is that this tilting of the potential energy surface towards lower or higher density is kind of physical, and I'll come back to that later. Then what you can see here is that there are kind of 3 peaks in this distribution. So at the top of this rightmost peak is the diamond and the hexagonal diamond, which is also experimentally realized structure in elemental silicon. But then these that appear at the top of these other peaks are known high pressure phases. And again, if in the Boltzmann factor you put the enthalpy and then start increasing the pressure to, let's say, 4 gigapascals, then you see that the probability distribution will start favoring denser structures. So they will kind of grow in probability, so that at about 10 gigapascals, the leftmost peak will now become dominant in terms of probability. And again, this corresponds fairly well with the transition pressures for these structures here that are observed experimentally. So this is kind of an accident that these pressures, where you see probabilities overcoming other probabilities, correspond well to experimentally measured pressures. I still have no real explanation for that, but that's just an observation that every time we get a situation like this, we seem to be reproducing transition pressure fairly well without even plotting equations of state and doing the common tangent just from the probabilities alone. But I'll leave that open at the moment. All right, so hopefully I provided in these couple of examples some convincing arguments that one can resolve the conundrum of having many low energy local minima, whereas only few are experimentally observed, by introducing this size of the local minima or their widths as some kind of a ranking parameter that will then distinguish those that are more realizable and those that are less realizable. Depending on what you actually are working with in the actual experimental situation, one can choose to have purely statistical representation of the potential energy surface, where you're just dealing with the sizes of the local minima, or you could choose also to introduce energy and then rank things based on fully, ensemble probabilities and see how that looks like. However, one cannot really talk about metastability without talking about lifetimes, because the metastability is much more connected to the time than to the energy, actually. So the local minimum can still be very wide but very shallow, and in that sense very short-lived, hence not exactly experimentally realizable. So the next really order of business, if one wants to complete the picture of metastable materials discovery, is to talk about lifetimes. This is another relatively old topic. I mean, it goes to the topic of phase transitions. Now we are talking about solid-solid phase transitions. But the question that we are asking here is a slightly different one. Instead of focusing on every detail of one particular phase transformation mechanism, we are asking the question of how can we identify out of this collection of local minima that we are finding using random sampling, how can we identify those that will live longer? And that, even if we can create some kind of a qualitative scheme to classify polymorphs into short and long-lived, that would be tremendously useful. And it will get us a long way into metastable materials discovery. And then if you go back into the literature and then search whether have people previously been doing something similar, you find in the 50s that Berger kind of tried classifying at the time known polymorphic or solid-solid phase transformations for crystalline phases into short and long-lived based on purely crystallographic arguments. So his classification is more complicated than what I'm going to say, but for the sake of time, I'm just going to say it briefly. Basically, if you know of a simple deformation, the Bain-like path between two structures, then the likelihood of that transformation being fast is high. And if such a deformation does not exist, then the likelihood of the transformation being slow is then high. Again, Berger did it on, at the time, known transformation mechanisms or investigated ones where people have been proposing various deformation mechanisms. So really the first order of business is creating those deformation for the two arbitrary structures. And that problem of creating those deformations has not exactly, to my knowledge, been solved. And that problem goes into the mapping, like the geometric problem of mapping infinite periodic arrays of points onto each other. So we did this, started working on it a couple of years ago. I had a very talented student who kind of thought it through, and we created an iterative procedure to map periodic arrays of points onto each other that I'm going to talk a little bit about and describe a little bit about. The algorithm that we developed kind of consists of two parts, and I will let you talk first about this first part, where we will take the two structures, crystalline structures, let's say the initial and the final one, and we will try to map atoms from one to the other, creating some kind of trajectories of atoms from one structure to the other. And the function that we are going to minimize or optimize in this is just the total distance atoms need to travel. So the length of each trajectory, so the total length of the trajectories of all the atoms. So this problem does not scale very well. So it's a factorially scaling problem if you are trying to map and establish correspondence between the atoms of two structures. But fortunately for us, that problem has been solved before. So this correspondence between two sets of whatever objects is usually called the assignment problem. And it appears, for example, in situations where a taxi company is trying to decide which taxi that is in the streets. Let's say you have 100 taxis and 100 customers looking for a taxi, or an Uber these days. Like which car will be assigned to which customer in order to minimize the distance. So basically, the closest car to each customer. That problem shows up in many different contexts when you need to assign works to workers and so on. And it has been solved before by mathematicians, and the algorithm that solves this problem without factorial scaling is called Kuhn-Mankres or Hungarian algorithm. And our algorithm to map crystal structures will use this solution. And there is another choice that one needs to make when mapping crystal structures onto each other. The choice is really whether to include periodic boundary conditions or not. So our code can do either one. And I will tell you first about what happens if you include periodicity, and then what happens if you exclude periodic boundary conditions, and then map these arrays of points as just big arrays of points without any periodicity. So in case you choose to include periodicity or periodic boundary conditions, the choice of the periodic cell in the algorithm, and the results that I will show you will do that, is the cell that is the lowest common multiple of the two, of the initial and the final structure. And if you choose that, that's the smallest cell that you can actually choose to establish this correspondence. That result is kind of equivalent to what people from Bilbao crystallographic server would call maximal symmetry transformation patterns. So this algorithm will then create something akin to Bain path for martensitic transformations. And I will show you just how that works on a little movie. So you choose sections of the crystal. In the first part, you choose some random relative positions, map to minimize the distance, move, like rigid transformations are allowed, rotations and translations, remap, choose another relative position, map, move to minimize the distance, remap, and this is the actual solution for this particular case. And now when the algorithm finishes, it will have the correspondence between atoms established. So you will have a trajectory, like a vector, pointing from each atom to its corresponding atom in a different structure that then you can discretize and then make pictures. So we are back now at known experimental polymorphs of silicon carbide. I'm just showing you what this algorithm produces. So there are 3 known polymorphs of silicon carbide, just to remind you. Space group 186 is wurtzite, 160 is the rhombohedral, and space group 225, which is the rock salt. And these are kind of the Bain mechanisms that our algorithm finds for the transformation from wurtzite to rhombohedral, rhombohedral to zinc blende, wurtzite to zinc blende, and rock salt to the other 3. So 4 polymorphs, sorry, rock salt is included. And again, we are looking for some qualitative way of distinguishing whether the transformation is likely to be fast or slow. So then once discretized, this transformation mechanism, you can then calculate using first principles method, just the static energy of each of these snapshots, each of these images. And what you're seeing here are the plots or the energy profiles along these pathways. And the 3 upper panels will show some kind of estimated barrier for those transformations, and the 3 lower will have their barriers much lower in energy. Like, these are kind of approximate barriers, much lower in energy than the upper ones. And again, if you compare this to experimentally known facts, you will find that these tetrahedrally coordinated structures, meaning wurtzite, rhombohedral, and zinc blende, are all long-lived metastable phases. So they can be stabilized. And these magnitudes of the barriers of, like, in the order of about half a volt, 300 millivolts per atom, are usually, when it comes to bulk barriers, considered to be high. Whereas if you go to the rock salt, and the barriers related to the transformation of rock salt into these other tetrahedrally coordinated structure, rock salt is octahedrally coordinated, then the barriers are much smaller in magnitude. So basically by a factor of 4, and they're all around 100 millivolts per atom or less. And this is usually, if you are looking for qualitative discussions in the literature of these, under quotations, bulk barriers, the 100 millivolt is usually used as a rule of thumb for distinguishing whether something is going to be slow or fast in terms of kinetics of the transformation. So we are again reproducing fairly well, this picture reproduces fairly well the known experimental fact that the high pressure phase, which is rock salt, once when you release the pressure, is going to live very short and transform quickly into the other ones, whereas the tetrahedrally coordinated ones are going to live long. And these are the upper ones are actual metastable phases.
So I have a question here.
Yes.
So here's the top row, the left and the right limit has essentially the same energy, if I'm not mistaken, and that makes
almost the same, yes.
And that makes the barrier big, but in the bottom row, one is much higher in energy, and that is reminiscent to what happens near first order phase transitions. If you push one energy up, then you will get to the spinodal point. Well, it will become unstable, but it automatically makes the barrier smaller. And
Correct.
I was wondering if you can relate the barrier size to the difference in energy between the 2 states.
You probably could, and chemists even have a principle which is called so there is some principle, I forgot the name of the principle, that says that if the energy difference between 2 states is high, the barrier is usually low. Mm-hmm. So I think, yes, you have a point there. We just haven't accumulated enough statistics for this to be able to just show it and show, are there any outliers potentially?
So, in other words, if you could fit these curves by a quartic function, like in simple Landau theory,
sure,
then there will be a very straightforward connection between the difference in energy and the barrier height.
Okay, I mean, let's talk more about that. Yes, I agree. We should certainly investigate these things more. And the energy difference, you are right about that. So the tetrahedrally coordinated polymorphs are actually very close in energy to each other. So it's a well-known fact that every zinc blende semiconductor, you could grow as a wurtzite and it kind of is a stable phase, it's not a problem. Or every wurtzite can be grown as zinc blende and this rhombohedral, and they live, whereas the rock salt seems to be a short-lived high pressure phase. There is another thing that we kind of noticed from this plot is that rock salt somehow transforms quickly into any of these three, rhombohedral, wurtzite, and zinc blende. So we asked a more broader question about rock salts in general. So if this can be generalized, this rock salt transforming quickly into the others, then even if you were kind of to shift the energy, and let's say you make a rock salt ground state and 160 an excited state or higher energy state, this geometric transformation would remain the same, and the barrier likely would remain low. So then the question was really, if we investigate all the rock salts, so all the systems with the rock salt ground state, do we find polymorphs? And this is the result of our literature review, pretty much, where we investigated all A1, B1 compounds, searching for those that crystallize in their ground state as rock salt. So there are about 700 total in various databases of A1, B1s. 36% of those, about 240, are actually known to crystallize as rock salts in their ground state. By the way, A1, B1 is the largest known group of compounds by far, and the rock salts is the largest group of compounds, even beyond binaries, that all crystallize in one crystal structure. So this is kind of statistics. Out of 700, 240 goes to space group 2 to 5, and this is kind of the distribution of the other crystal structures. And if you then focus on these and start looking for reports of metastable polymorphs, you find literally for all 240, for majority of them, you find nothing. And for a smaller subset, you actually find only 4 crystal structures that are in addition to rock salt that have ever been reported. So the cesium chloride type, the wurtzite, the nickelin, so nickel arsenide, and this potassium hydroxide. And it is known from experiments that these 4 will all transform quickly into rock salt. So cesium chloride is a known high pressure phase of rock salt. Wurtzite is known, as I showed you just a moment ago, to transform that rock salt transform quickly into wurtzite or the other way around. Nickelin is the same. So essentially, all these 240 that crystallize in their ground states as rock salt don't really have any metastable phases. So they are all, if they have metastable, if they have higher energy structures that have been observed, they are all short-lived. So that's the point. So then we said, can we then apply our, both random structure sampling to identify which local minima are statistically more relevant, hence more realizable, and can we then apply our mapping algorithm with periodic boundary conditions, like the one that I showed you a moment ago, to identify, are there local minima that could potentially be long-lived? And we studied 3 systems: magnesium oxide, tantalum carbide, and lead telluride. And we basically took all the statistically relevant local minima that we found and applied the mapping algorithm, and then did this barrier estimation, or the bulk barrier estimation. So in the case of magnesium oxide, we find the largest number of, let's say, more symmetric, not space group 1 local minima. So these are the space group numbers. And these are the energy profiles of them going into rock salt. On y-axis now, we divide the energy with the melting point of the rock salt magnesium oxide, just to express everything relative to the melting point so that we can kind of discuss the kinetics a little bit. And what we find is that all the barriers are pretty much within, I think for magnesium oxide, around 30% of the melting point. So even with this relatively crude barrier estimation, we find that all statistically, hence more realizable local minima, will transform quickly at typical synthesis temperature into the rock salt. So this again corresponds very well to the observed fact that rock salt is the only realized structure in magnesium oxide. So not only that's the widest local minimum, but all the other relevant local minima will transform quickly and hence can be added to the rock salt local minimum. So in aggregate, rock salt local minimum expands beyond what we saw before. For tantalum carbide, we actually find much fewer local minima, and then the highest barrier we find, or we estimate, is within 40% of the melting point. So again, at typical synthesis temperatures that we are going to be relatively close to the melting point, nothing will survive, and rock salt will again be the only one realized. And then for lead telluride, we literally find only 2 local minima in addition to rock salt that are more statistically relevant, and the result is pretty much the same. So this again adds to our discussion of magnesium oxide from the beginning, and pretty much explains why we don't see polymorphism or metastable structures in binary rock salts, by extension, of course, from these three systems. So I just want to spend a few minutes to tell you what happens if you exclude periodicity, because that's another very interesting result. So one could do this distance minimization by cutting out large spheres of each crystal structures and then map them without any periodicity included. And then find the periodicity after the fact. So pretty much the second part of our algorithm, if you choose not to work with periodic boundary conditions, will then be finding any periodic pattern that one can potentially see in the mechanism that is now produced without any periodicity included. So just to not spend too much words, I'll again show you a movie. This is the starting point. So you have the mapping already established. And typically the arrows or the displacement vectors will then diverge if the volumes of two structures are different, which is usually the case. Then if you include strain, so now you are allowing for the fixed mapping a strain of one structure relative to the other. So then the arrows will then shrink, the strain, allowing strain will then cancel the divergence. And then you can analyze the array of the displacement vectors and then try to find some kind of periodic pattern in there, which in this little movie you can see the box. So this will produce, depending on the sizes of these spheres, different results. And for the most part, for those prototypical kind of transformation mechanisms that people were discussing before, we kind of produce results that are either exactly the same or very similar to what people have been found, with one notable exception, and that's the actual martensitic transformation in martensiting steels. So this is the famous FCC to BCC or austenite to martensite phase transformation. And in the left panel, I will show you what you get if you try to minimize the total displacements of atoms without periodicity and then recover periodicity after the fact. So I will play you a little movie that this transformation from FCC to BCC in this left panel is kind of shown from different angles. And this is the periodic box or the scale of that transformation that we find. So it's much bigger than the Bain mechanism that was proposed by Bain before. And if you look at this panel, the top right panel, what you find is this slipping process that happens. So there are slabs within which the Bain mechanism was actually found, but then the slabs kind of slip between each other. And that slipping mechanism basically is a product of the abandoning periodic boundary conditions, then minimizing pretty much the global strain. So a little bit better picture is then shown in the right panel, a more detailed, not a better, where you can see exactly the box in relation to the conventional unit cell that is shown in kind of this lighter color, and then the mapping. So atoms are indexed based on the mapping. And then you can ask, okay, fine, but what is then the direction of this slipping process? So the slipping process can be described by the Miller vector 112 expressed in the BCC basis. And you can see what the slipping actually produces. So this kind of plane that is shown highlighted in black, basically breaks down due to the slipping process. Another just kind of description of why we find slip. So this is the classic Bain transformation mechanism that you find this picture of this in any book on kind of crystallographic aspects of phase transformations. So pretty much in the BCC structure, you find this pattern that looks like FCC, just not a cube. And then by deforming the structure to make it a cube, FCC, sorry, on the left. And then by deforming the structure, you actually find the BCC. But this transformation will introduce a really large amount of strain. And that's why it has not actually been observed experimentally. And our mechanism can be explained like this. So the Bain distortion will produce a very large strain, but then the slipping process will pretty much slide these slabs relative to each other and then minimize the global strain. So that's why the slipping happens. And you can then go into the experimental literature and look for evidences and what is known experimentally. So these are the two pictures of martensitic steels after the transformation from FCC to BCC has happened. So basically austenite has transformed into martensite. And in the left picture, what you find are these kind of lines, which are called Newman bands, which are twin boundaries. And these twin boundaries are related to, like slipping and twinning is a related process, because you could choose in our mechanism shown on the previous slide to transform one of these slabs in like mirror plane transformed to on itself. So then in the final structure, it will actually produce a twin boundary. And if you ask what is the direction of these twin boundaries, you find 1, 1, 2 in the BCC basis, which is exactly the slip that we found. You find it in this other picture as well. And what I haven't told you about, but you can read in our paper from a couple of years ago, is that our mechanism also produces most often experimentally observed orientation relationships between two phases, which are called Kurdzimov-Sachs orientation relationships, or KS, and also the habit plane between these two crystal structures, so the coexistence plane, which is 252, which you can also see in this picture. So to my understanding of the field, I'm not exactly a metallurgist, but I sit in a metallurgy department. This is the first model that does not include any adjustable parameters that are then or experimental information, except the two lattice constants, that produces almost all frequently observed experimental facts about this phase transformation, which was kind of a very nice and somewhat unexpected result, and all a consequence of minimizing the displacements of atoms without including periodicity.
So Vladan, this is
Yes.
also relevant for plasticity, I believe, right? When you strain the crystals, you want to change the aspect ratio, and then you have to do this through these twin boundaries and dislocations.
Correct. Yes.
Oh.
I agree. It has relationship to how to dislocations and all that stuff. Again, this was something that we just stumbled across, and we felt obliged to kind of investigate it a little bit further, but it's not really what we mainly do. So there are certainly questions that we can then investigate deeper and all that.
Okay.
And again, it's a relatively recent result that requires more attention. I agree.
You know, I recently learned about all this because, you know, the slipping between planes is something that probably is much affected, that is very different in a elemental metal and in a high entropy alloy.
I agree.
It's an internal kind of mechanism, which so that would be actually interesting to you know, expand this discussion.
So these kinds of martensitic transformations, but like the really the FCC and BCC, are also appearing in many alloys and in high entropy alloys as well. And it is known that the kinetics changes depending on chemical composition. There are also shape memory alloys that pretty much work following some of these transformation mechanisms. So there is kind of a lot of phenomena that could potentially be investigated using using this algorithm and see how well it reproduces all that stuff. So yes, I agree. So, and in high entropy alloys, that I think very pertinent, how these locations move and how these slipping processes happen, because you can manipulate them with chemical composition. All right, so this was already fairly long. I want to kind of spend just a few minutes to tell you about a couple of other unintended consequences that we bumped into when doing these things. So the first one has to do with random structure sampling, actually. So I just want to remind you of these probability distributions for elemental silicon. So this is the slide that I showed you before. So we used them originally just for ranking different polymorphs based on this realizability concept. But when you have probability distributions, you can then ask yourself, okay, what if I were to average various physical quantities using these probability distribution? Because that's the, one of the basic things you do when you have a probability distribution. And if you start averaging, then what physically that would represent some kind of mixed state of all these different local minima. And potentially that could be used, as Vlad alluded to at the beginning, as some kind of representation of an amorphous structure. And in order to investigate that a little bit further, so the two quantities that we averaged first were just the long range order and short range order quantities. The first one was just the X-ray diffraction, so the modeled powder X-ray diffraction. And because we are doing ensemble averaging, we can do that at low temperature and at high temperature. So this is just an equation how one would average modeled X-ray diffraction pattern. So basically what we do, we take these 10,000 or so 9,000 something local minima that we identified. We would calculate X-ray diffraction pattern for each one, and then just average them according to the rules of classical statistical mechanics. And at low temperature, of course, it is the ground state that dominates. So you see the crystalline features of diamond silicon, so nothing unexpected there. And at high temperature, you find this mixed phase, where now all these X-ray diffraction patterns are mixed together. And of course, the long range order will melt. And what you will find is this kind of features, these broad humps in the average X-ray diffraction pattern. So what you can then do, or what we did, is go into the literature looking for X-ray diffraction data on amorphous silicon. And we do indeed find these two broad features that have been identified experimentally, and the correspondence between what we find and what experimental finds is, in my view, fairly good. And just to clarify this further, so this has not been done as usually would be done on a large supercell. This has been done on having a relatively large set of small cells, where each cell represents a local minimum obtained through this random structure sampling, followed by first principles relaxation and then average. So we can then go and then average the short range order quantities. One of them is the PDF, so pair distribution function. And again, low temperature average would resemble a crystalline phase, and then the high temperature would be liquid-like or amorphous-like. Again, amorphous silicon experimental values correspond fairly well what we predict. Another quantity that is usually discussed is the density or the volume. So what you see here is just the average volume as a function of the temperature used in averaging, and how it depends on temperature. So at low temperatures, of course, you get the volume of the ground state diamond silicon. So this is just the ratio of average volume relative to the ground state volume, and you get some kind of a crystalline phase at low temperatures. And then as the temperature increases, the volume goes down, meaning the mixed state is denser than the crystalline phase. And by the way, that's a consequence of the distribution tilting to lower densities, if you remember that discussion. So for silicon, you would the distribution or all those points were kind of tilting to the denser structures from the diamond. So then the mixture will then have, as an average, lower volume. And we then went and found the experimental result for the liquid silicon. So liquid silicon is known for the same anomaly like water, is that the liquid silicon is actually denser than the crystalline phase. And then the same ratio that you found from experimental results, like volume of the liquid divided by volume of the crystalline phase, where volume of the liquid is taken at the melting point, corresponds to about 1% to our average volume. So this prompted us to kind of think a little bit further into what this all means and whether we could represent glasses, basically frozen liquids, using this methodology. And it seems from these results on silicon that our statistical ensemble in the high temperature limit could be understood as a representation of the glassy state. Why a glassy state? In my view, again, now we are entering the territory of philosophy. In my view, what we have is the fully ergodic system, so ergodicity completely assumed over all these local minima, but without kinetic energy. So in that sense, in my view, our ensemble picture or the collection of these local minima could be understood as an infinitely quickly quenched liquid. And in order to test that hypothesis, I will just show you the results on the actual glass. Silicon is kind of amorphous. It's not exactly, doesn't undergo a glass transition. So this is our very recent result on the structural properties of SiO2 that then we modeled using, again, a large collection, 3,000 in this case, of 24 atom cells. And what I'm plotting on the left is the structure factor, modeled as measured by neutron diffraction or X-ray diffraction experiments. And it's not exactly the structure factor, it's the actual QS of Q minus 1, the quantity that when you Fourier transform it, you get what is called the reduced PDF. So on the right panel shows the quantity called the reduced pair distribution function. That is the direct sine Fourier transform of this quantity. And in orange, you find the directly calculated from our real space structures. And then in red, what you find is doing Fourier transform on the left curve as experiments would do, and how well these things agree with experimental results. So in red is our result, in purple is experiments. So if you go to directly measured quantities, which is the structure factor, the correspondence between peaks and their positions and their intensities is fairly good. The only, let's say, exception to that is this first peak. And as we discuss in this paper, this is I think the price we need to pay for small cells. So we are doing 24 atom cells. So this small peak has to do with, order or atom-atom correlations, if you wish, at about 10 angstroms and further. And you can see that from this picture that within like 6-7 angstroms, the pair distribution function is reproduced again fairly well. So where this first peak kind of enters is the density. We have about 2.5% in interatomic distances error relative to experiments, which again is expected from first principles methods. And another thing that this first peak in experiment is usually in literature related to are larger voids of the radius of about 10 angstroms or larger that could be present in SiO2 as a consequence of the glass transition that we just don't reproduce that well with 24 atoms. But other than that first peak, everything else is, at least to my taste, reproduced fairly well. And another thing that's kind of an interesting use case for this method is then calculating properties of glasses without having to deal with large supercells. So properties are due to nearsightedness of electronic matter. kind of determined on a shorter scale. So even if we are not able to get those large voids right, the hope is that we can get other properties right. And what I'm showing you here is now ensemble average, the electronic density of states, calculated as, again, an average over the densities of states of the collection of these structures. And this is the black curve on the left, and then the two experimental results that we found in the literature, both UPS photoemission measurements measured in sometime in the 70s at TJ Watson, IBM labs. And again, the correspondence with experiments of our average result is kind of fairly good, or at least within the differences that you find in the literature of between different experiments. This is a very interesting result because you could, in principle, now imagine calculating electronic structure of disordered systems in general through this collection of small cell local minima, and which would then enable high accuracy electronic structure calculations. This is all done, what you are seeing now at the DFT level, but what we are doing right now is calculating using many body methods like GW and Bethe-Salpeter equation to actually calculate optical properties of SiO2 and also have better calculation of electronic properties.
Excuse me, why the experiment says this is a metal? You have a denser states.
First, this is experiment. The blue one doesn't really. It's the orange.
No, the orange one, yeah.
The orange one, I think, is just either. I still cannot in that paper find out the reasons why it's different than the blue one, but the orange is, I think, just sputtering. So they grew thin film just by sputtering, and then I think it's not exactly a glass, so it has many more reasons for it's basically a lower quality film. I think that's my interpretation. Whereas the blue one is again a film, but it's thermally grown somehow. I don't really understand how, but I think this is much closer to a glass than the orange one. And they don't get access to conduction bands. So I don't know, we do still have, in our case, underestimation of the band gap. So I assume that this conduction band feature is pushed in reality to somewhere here. So our band gap, if you measure it from somehow on our curve, is on the order of like 4 volts, whereas in experiment is about 9. So the underestimation of DFT of the band gap of our result is pretty severe. So I think orange curve, probably the gap is not closed. Does that answer?
Yeah,
okay.
Thank you. Yeah.
All right. So there is one thing, in order to really enable high accuracy calculations, you really cannot do GW on 3000 structures. So we did then the follow-up exercise where we said, okay, let's take the 3000 result as a reference, and then let's pick randomly 100 of those and see how well the density of states is reproduced, the average one, by just averaging over just a sample of 100. And then we did this 100 times. So with this gray kind of band that you see around black is pretty much the 100 curves, which are all evaluated as the average over 100 samples of 100 structures. So again, we don't see this as a big deviation from the reference, from the black. And one could, in principle, just pick 100 structures and get lower accuracy result, but still very reasonably within experimental measurements. And in order to prove that 100 structures may actually be enough to calculate other properties, we calculated the bulk modulus now using 100 structures total. So we calculated the 100, like we took sample of 100 from 3000 randomly, and we calculated the bulk modulus of each one of those. And the histogram of bulk moduli is shown in gray, but now averaging procedure is a little bit complicated. I'm not going to go into the details of it. Basically, you consider our mixture as a composite of local environments represented by each of these 100 structures, and then from the theory of elasticity, you can find two limits for composites. One is called the Royce and the other one is called the Voigt limit, which we can calculate. We can then use central limit theorem to estimate error bars on these limits, because we are taking 100 out of a 3000. So what you see in blue is kind of the confidence interval, 1 sigma pretty much for the Royce and 1 sigma for the Voigt. And they are like the result that we would call a bulk modulus of a glass. They go somewhere between like 39, which is the lower value of this confidence interval, to about 46, which is the upper value here. The experimental results for glass, for SiO2 glass, range between 36 and 39 gigapascals. So again, we are reproducing the bulk modulus using this scheme of the glassy SiO2 within typical errors of about 10% that DFT methods usually make in bulk modulus. So this is where the story kind of ends, not ends, but we are still working on investigating other properties, as I said, doing many body calculations for electronic structure and see how all that pans out. I'm going to skip the interface part. Just want to say in really 2 sentences, you can adapt our structure matching procedure for phase transitions into structure matching procedure for 2D structures, and then do some interface modeling. It seems promising. We are able to reproduce these kind of TEM images for nickel on yttrium stabilized zirconia, silicon grown on silicon carbide. You can then use this to predict Schottky barriers, let's say between gallium oxide and platinum. So this is the local density of states on one of those interface structures, calculated using hybrid functionals, so HSE functional, a little bit better representation of band gaps. And you recover Schottky barriers that are very close to experimental results using these techniques. And conclusion kind of reiterates the stuff that I already said, so I'm not going to spend time on the conclusion. I just want to go and give credit where credit is due. So this is my group, the picture from this like a couple of months ago. My student Drew, who just graduated, was unable to join the picture taking ceremony, if you wish. So now he's represented here by just his head. And I would like to also acknowledge the funding sources for most of this work. So NSF, Department of Energy, some internal grants of NREL, and computational resources that come from NREL, the local Colorado School of Mines, and the PATH Consortium. And thank you very much.
Well, thank you very much, Vladan, for this fascinating presentation. Are there any questions now?
Yes, I have some about the method you create your random samples. How are you going about that? That wasn't totally clear.
Okay, I can give you. I mean, it's written in our papers in details, but I can give you a short description of how it works. So you would use. It's written in Python, so you would use a random number generator to generate A, B, and C lattice parameters. So basically the size of the box. And they will be chosen between 0.8 and 1.6 in the units of a global scale of the star. So those are the boundaries that will be put on the random number generator. And then we would choose alpha, beta, and gamma from, if I recall correctly, 40 degrees to about 120 degrees. Again, those are the bounds that were chosen based on testing. And again, there are years of testing behind all this stuff that I presented here. And then one will create a grid of points. So you will discretize, so we will discretize, the code will discretize the space inside this box that we just did, and created a grid of points. And then to place atom number 1 randomly, we would again use a random number generator to just choose one grid point and put it there. Then we would create a probability distribution by placing a Gaussian on that grid, occupied grid point. And then the next atom will be placed by choosing randomly among the grid points that have the value of that Gaussian below certain threshold. So that threshold is again an input parameter. And that will then favor the grid points that are away from the one that you just occupied. In that sense,
okay, sort of, it's some type of stratified sampling of your.
You can call it something like that, but again, we were trying to go for as homogeneous distribution throughout the cell as possible. So I think it's a waste of computer resources and time to go and investigate structures that have one side of the box completely empty and one side of the box completely filled. You also want to prevent atoms on being too close to each other, because then relaxations will be problematic because the forces will be gigantic. The structure may just explode in the relaxation. So this was all kind of, let's call it, these are reasonable assumptions while still preserving some degree of, or large degree of randomness, let's say, inside these structures.
So I was also wondering if, as you then explore your probability distributions at different temperatures, what you're doing would compare to an approach like, say, particle filtering.
I'm not sure I understand exactly what you mean by particle filtering.
Oh, it also goes under the name of sequential Monte Carlo.
All right.
So it's a Bayesian approach of basically taking as your prior distribution at some higher temperature and deriving a distribution at a lower temperature.
Understood. I mean, the goal here is not really to use to not be too clever. So the goal here is really to provide a statistical representation of the potential energy surface and nothing more. So that was the goal. And I want as homogeneous of a rain, if I can use that analogy again, as possible, in order to just sample the potential energy surface in order to be able to measure these widths. I'm not sure that any of the processes like Monte Carlo or there is, how is it called, the Parinello's thing, that's the metadynamics or things like that, will give you the completely unbiased overview of the potential energy surface, if that makes sense.
Okay, yeah.
So I guess you choose this 40 atom structure, so you end up having like 20,000 random structure. Of course, you can choose a lot other number of atoms. Okay,
sure.
The more number of atoms, more random structure you're going to have. End up. So why is it choose 40? So.
Okay, so there is a little bit of assumptions. I mean, your question is correct. That is implicit in all this stuff. There is a theorem proved by Stillinger, I believe, about exponential growth of the number of local minima with number of atoms. Okay, so at some point you will hit an exponential wall and you will not be able to converge your random sampling. So random sampling is not easy to converge, and there are two convergence tests that one needs to run. One is for every chosen size, one needs to converge the frequencies of occurrence essentially, and then you need to converge the qualitative picture that you are obtaining for one size. You need to converge with respect to the actual size. And one needs to understand that as you increase the size, the number of possibilities grows exponentially, such that all the frequencies of occurrence will go down. But if qualitatively the highest frequency structures remain highest frequency structures, then we call that converged with respect to the size. But depending on the system, for some systems, you converge it with 24 atoms, for some systems with less. One also needs to be careful not to over-represent certain structures relative to the other. how we picked n equal 12 here, because we knew that all known polymorphs are commensurate with 12 modules. This is again just a proof of concept picture. This is not a picture where we are trying to predict new polymorphs. So in that sense, this choice here is good enough. But if we want to predict new polymorphs, then you need to be much more thorough in size dependence and all that stuff, which we do. Is just that I wasn't going into technicalities in this particular talk. But yes, correct, good question. One needs to be very careful about converging all these things.
Thank you. Yeah.
Mm-hmm.
Any other questions?
We're still recording?
Yes, we're still recording. I can stop recording if you want.
Stop
okay,
recording.
I'll stop.